that's the reason I would like to give you your midterm back. You look at it and let me know if I made any mistake on your grading or anything. You can come back and talk to me, But very quick. Several of you send me an email. What do you think I should do to pass the final? It's not me. It's you guys. Whatever. You know what you did in your midterm. Those ones they did good, so they know what they should do to get a good grade. Those ones they didn't do good, they know what they didn't do. How much did they study? How much did they practice? That's very simple. If you do the same thing, you're not fail. Very simple. So if you're going to change your attitude and work, you don't have very much of time. Next week is the final exam, and it's already technical like a C minus. I don't know, C plus. It's not difficult. But in my life, never ever I shoot for C minus. You know what I'm saying? I'll shoot all this for A plus. That's my goal. Not C minus. C minus, I don't want to say what I'll say. It's for losers. No, I'm not saying those ones are getting the C minus. Those ones they shoot for the C minus. Yeah, sometimes you study hard, even something goes wrong in your exam. I don't know, you feel bad, you're sick, something happens, you know what I'm saying? It has happened to me also, it's C minus. I'm not calling those people C minus. Those ones, they shoot for C minus, I call them. Those ones, their target is C minus, but they are losing, That's my point. It happens to people who not get a grade, but it could be different reasons, for that. And my point is, if you study well, and still, even you had a 2, 3, they were very low, but the rest, they were in the range of, they can maybe, if they can get a good grade, even if still they can go even maybe B minus, something like that, and still they have that chance. But it's all up. I want to finish, I have 2 more things to teach, quick, very quick, not that much. And I'm going to go through examples. Hopefully I can go through 3 more examples today with the discussion session, and we'll wrap up this thing. We talked about the power flow for the transmission line, short transmission line. If you remember that, we said that short transmission line has R and X. We calculated P and Q. I think I calculated on the receiving end. I'm not sure in the receiving end or on sending end. I'm not sure which side did I calculate. You can calculate it on the other side yourself. But now, let's assume we have a transmission line. I'll call this one A, B, C, E, VS, IS, VR, IR, right? This is general. It could be a medium line. It could be a long line. Long line, you remember? We had a pi model, right? A nominal pi model and nominal t model. And also we had the ABCD for all models. It doesn't matter which model it is. Is it short, is it medium, is it long? For all of them, they had this one, right? I'm going to calculate the power equation based on the ABCD equation. ABCD value. One thing I forgot to say, we know for all this one, A is equal to D. You can go check everything for all the one we calculated already. A is equal to D. And one thing I forgot to tell you, AD for all cases, minus BC is equal to 1. This is valid for any transmission line. This for these 2 equations we have is valid for any transmission line. Now, my intention is to calculate the PSQS. Let's say here, I have a PS plus JQS, and we call it SS. And here we have a SR, is a PR plus JQR. My intention is to calculate, to come up with the equation for these values. How much is PS, how much is the PR, how much is the QS, how much is the QR. Before going there, it's very simple. It said, how much is the SS? How much is the SS? I'll do it for either single phase system or one phase of a 3-phase system, right? What I'm writing here is for either one phase, we can time it by 3 to calculate 3-phase, or a single phase system. Maybe we have a single, not maybe, definitely we have a single phase system. system in the telecommunication. You have a single phase system for the power transfer and those kind of things. So SS is a VS IS conjugate, right? And SR is a VR IR conjugate, right? Basically, if we know the IS and IR and replace it in this equation, because usually VS and VR, they are known. They are known values. If I can calculate VS and VR, sorry, IS and IR, replace it here, I can get my equation. Let's go back. Before going now, I need to calculate IS and IR based in a function of VS and VR. From the transmission line, we know VS IS is equal to A, B, C, D times VR IR, right? Let's do it. So basically, VS is equal to AVR plus B IR and VIS is equal to CVR plus DIR. Just timing this matrix to this vector, right? From here, I'm going to find IR. How much is the IR? From this one, I can say. It's going to be 1 over B VS minus A over B VR, right? So I know the IR based on the VS and VR. I want to calculate IS based on those two values. I replaced IR by this one, right? So basically, IS is going to, let's call this one 1 and call this one 2. 1 is so IS is going to be CVR plus DIR. It's going to be D over B DS minus DA over D VR. Let's factor in the, so it's going to be D over B VS plus C minus D over B VR. Right? So here, this one is going to be CB, CB minus AB over B, right? CB minus AD is equal to what? Minus 1, right? So I replace this one with minus 1, so I'm going to have this. I'm going to have IR is equal to 1 over B VS minus A over B VR. IS is equal to D over B VS. So that one is going to be minus 1. It's going to be minus 1 over B VR. Right? Minus 1 over B. So I calculated IR and IS. Now I can replace them in this equation. I'm not going to go through the detail anymore. I can replace this one to this equation, right? And I can calculate my SS and SR. I don't want to spend time on those kind of things. Just let me write the final answer. Look, I want to solve an example on that one. So, and you can write the equation on your cheat sheet. I'm going to give you the example. But don't rely a lot on your cheat sheet. Your cheat sheet is just for, I forgot this one. That's for that. Not to put all your notes on one page. You know what I'm saying? Cheat sheet is just for you to remind you, oh, I forgot all this equation. Now this one. You know what I'm saying? Not to try to write all your notes in one cheat sheet. Because after that in the exam, they're going to look at 4 down. It's not going to work. Just to tell you. You saw the cheat sheet. How much did you use it for the exam? This can be used a little bit more because we have lots of equations, here for inductance, for capacitance, for power, those kind of things, But I'm saying bring the cheat sheet with you, but don't rely on it a lot, Just try to, especially on the part is about the single line diagram, per unit system, short circuit calculation, those kind of. We don't need any cheat sheet. There is only one equation we need, We can to write that one. You are going to have one question on that one. The other question is going to be on the capacitance, the inductance calculation. That one maybe a little cheat sheet will have those kind of things. And we're going to have one on the transmission line. 3 to 4 questions, maximum 4 questions, or 3 to 4 questions we're going to have in the final. Now, if we replace this one over there, and actually we know A and D are equal, right? Basically, we can go and replace D with A. So, if we assume, let's assume, I'm going to put it on the bus bar structure. We have a BS with delta here. This is a transmission line, TL. This is a transmission line with a parameter A, B, C, D. And here, we have a receiving end. It's going to be, usually we select the receiving end as a reference, right? The angle for the load is 0. For transmission, for the sending end is going to be delta. We call this one also torque angle. If you remember, we call the delta torque angle. Basically, here there is a load, and here there is a source, right? So I want to, and here we have a PS plus JQS going this way, and here we have a PR plus JQR going this way. We could have another generator here also. Don't get me wrong. We could have another load here. In the example we are going to have those kind of things. Now, so I know the VS is this, VR is this. Basically, in this equation, look at here, we are going to have only A, B. D is again A, right? So I have two parameters. Let's assume A is A with alpha. A is A with alpha. This A is a complex vector. Remember, complex number, if you go look at it. I'm saying it's going to be a number like 10, 5, 2, whatever, with some angle. And B is going to be B with a spade. Just I assume these two, they are like this, alpha and beta, right? Now, I can replace these values here, right? I can calculate IRIS. I can calculate the conjugate of IR and IS, right? And I can replace it in this equation. Finally, I'm going to get to this equation. After, PR is going to be VS, VR. See, this is a VS, VR. This is a VS, and this is a VR. There is no angle, just numbers, right? VS, VR over V cosine of beta minus delta minus A over B VR to the power of 2 cosine of beta minus alpha. And QR is going to be VSVR divided by B sine of beta minus delta minus A over B VR squared sine of beta minus alpha. These are the PR, QR. If you have, so my point is, doesn't matter what kind of transmission line you have. So you can calculate the PR, QR knowing A, B, C, D values. You can go calculate this value. Now, PS, QS, they're going to be, PS, QS is going to be D over B, not D, sorry. D is going to be A again in this case. Let's put A here. A over B, VS squared, cosine of beta minus alpha, minus VS over minus VS VR over B sine of beta plus delta. These are the power equation, active and reactive power calculation for sending end and receiving end. For any transmission line, I use the ABCD parameters. I didn't use the short model or medium model or long model. I use the ABCD parameter to calculate this value. So that's one thing. I want to say, I'm going to solve two examples on this one. I'm going to move to that one to solve two examples on this case. Before going there, remember about the short circuit things we talked about in our Kelvin system. Usually those of you are going to get involved with the power system, calculation, those kind of things. If you look at it, just I'm throwing out this. For example, we have a power plant in San Diego, power plant, I don't know, in LA, power plant, I don't know, somewhere else. There is a grid here. These are the transmission line connected together. For example, this one connected here, I don't know, this one is connected here, this one is connected here. There is something like this. These are the either load or sources. These are, they call it bus bars, you know what I'm saying? And this is the grid. The grid, I think the US grid, the size of the grid, if you look at this node, I don't know what it is, about like maybe 1,000 nodes or maybe 1,000, maybe about like 10,000 nodes, you know what I'm saying? Think about how big is this? How big is this system? Because this one is going to end up with a matrix. A matrix is going to be defined based on how many nodes you have. For example, here we have a 3, 6. There's going to be 6 by 6 matrix to show all this system. Think about it, we have a 10,000 elements. It's going to be 10,000 by 10,000 matrix, right? But we're not going to go there. Why I'm saying this? The problem we are solving is very simple. Usually we have a 2 bus or maximum 3 bus because for calculation is too much, right? But I'm trying to remember the last one. Was it short circuit ratio or short circuit capability? Capacity, short circuit. Some they call it SCC, short circuit capacity. I have saw also they use the SCR, short circuit ratio. So for each bus, they put something here, SCC or SCR. For example, 10 MV. 10 MV. I want to tell you what, this is very important. For those when they want to work on the power system, for example, in General Atomics, I told you we had a short circuit and one of the line reactors, they went off, and now we need to replace that one. You have to do all the calculations to make sure the one you are replacing is as good as the first one. You can handle what we have. This number you will see is a very, very useful number. What does it say? Remember, we said Z is equal to V squared over S, right? V squared over S. So, in periodic system,
just really quick for PR, is it supposed to be VS over VR, VS VR over beta? Or is that...
No. These are all B.
Okay.
Beta is the angle. So these are B. If I wrote it similar, it looks like beta. These are all B, not beta.
Okay. And the same question for IR up above, right there?
Yeah, this is B.
Okay. Thought so.
Beta is the angle. It's just come to the sine and cosine, to the currency. So, what does this mean, this one? For every system.
For PS and QS, should it be D over D instead of A over D?
Yeah, it would be D, but the D is equal to A. You're right. D is equal to A. You're correct. It should be D. And if you want to put a D, put a D. Yeah, in the books also, in the book it says this is D. This one is D in the book. And this one is D. But D and A, they are the same. You know what I'm saying? You can put it out. I don't know why they put D when D and A, per unit system. Per unit system, the best advantage of per unit is you are working with a nominal voltage. You know, if you have one, it's a nominal voltage. A very, very good guess, if somebody asks, how much is the voltage at this outlet? We are going to work with per unit, right? How much is the voltage here? It's almost 1 per unit. The voltage is 110, right? The nominal is 110. Maybe the voltage will be a little bit more than 110, maybe it's 115, 120, right? Or a little bit less, it's going to be 105 or something like, or 110, right? So basically, 110 is the nominal voltage for this outlet, or 120, I'm not sure exactly, 100. So when you divide those numbers by 110 or 120, you get a very number close to 1, right? This is exactly the same thing for power plant. If you go divide the output of the generator voltage divided by rated voltage, it's going to be almost 1. So we don't talk about power flow. We talk a little bit here about power flow, but not really power flow study. When you have a big system, you have to use a numerical, method to solve those, 10,000 equations. You cannot solve it analytically. It's really difficult. So with the numerical method, I'm not sure if you guys have that course or not, numerical analysis or not. There is a Gauss Seidel, there is a Newton-Raphson, there is a Euler, there is a different method to solve those equations. For all those system methods, you have to select an initial answer. Say, hey, I guess the answer is this much. And what you say, okay, my answer is this much. Now I'm going to go use the one I guess. Go again calculate the answer. Right? The new answer, if my guess was good, perfectly good, I knew the answer. But usually you're not right? You have a guess, you go calculate it, there is a new answer, it's different from what you guessed, right? They define error. They say, okay, how much is the difference between this new answer and what you guessed? For example, 0.1. He said 0.1 is not good. I want to find my answer accurate by 0.0001. When the difference between my guess and the new answer is that much, less than that, I'm saying it's good, right? Now what you do, I guessed one thing, I put it in my equation, I went back, calculate the new answer. No, it's not there. The difference is bigger than what I'm thinking, right? You use the new answer as a guess. You go again, calculate it, another one. You go calculate it, another one, another one. If you go to the MATLAB, have you guys tried to put it like a third order equation or fifth order equation and just boom and give you the answer? It uses all these things to calculate those answers for that one. After the quadratic form, after that there is no analytical solution to say how much is the answer. They use all this numerical method to have. Now why I said this one, if you go back to the power system, we have a system like this, right? I want to calculate all the voltage like this. See, I want to know how much is the voltage, how much is the angle, how much is the voltage, how much is the angle. So you have to start with the initial guess. This is a numerical system to solve it. The initial guess is for all the voltage. For amplitude you select 1. For the angle you select 0. That's a very, very good, initial, guess. You don't believe how much is close to the final answer. But you use this one to do the calculation to finally get to where you want, right? But for us, somebody asked me, hey, if here is a short circuit, it's a huge system here. Somebody asked me, how much is the short circuit current here? This bus is, for example, 12 kV. This is a 12 kV bus. Somebody asked me, how much is the short circuit here? This guy is telling me how much is the Z here. I can go replace the whole system from here. I can go look at this system from this box and replace it with its Thevenin model. So how much is the Z Thevenin? It's going to be the voltage here, V over SCC. So basically, and now I can say, okay, let's forget all this green. This one is going to be modeled with this. This boss is the same boss here. This boss is the same boss here. Now, it's going to be impedance here, ZT, and its source here, 12 kV. is that voltage, right, divided by that impedance. That's the reason they call it short circuit capacity. Short circuit capacity. This is a very, if you saw at one point you get to the power system, company, utility company, you see this single line diagram, and you see like I don't know, 50 buses connected through the lines together, and you see some numbers written on this buses. These are the short circuit capacitors. If now think about it, let's say we are going to connect a motor here, right? We have to have a circuit breaker here, right? We have to have a circuit breaker. You need to calculate the rating for this circuit breaker. What is the rating? If short circuit happen here, right? You don't want the circuit breaker to blow up, right? So you go calculate the short circuit current here. You say, okay, if there's a short circuit current here, I'm going to see 5 kiloamps. So now the breaker I'm going to buy, it should be able to handle that much current. And usually those manufacturers, they will give you that one. How much this breaker can handle, you know what I'm saying? It's kind of like a data sheet reading, You know how much you need, and you go look at the data sheet, no, this one is not good, this one is good. My point is, this number is a very, very big number, very, very meaningful number, lots of information there. You can model a huge system, see? All this system is gone, and we replace it with this, with a simple system like this. So that's another thing I was going to tell you. The short circuit capacity or short circuit ratio, SCR or SCC. Short circuit capacity, I think, is more meaningful. This one is very, very important. And this one is for powerful for any transmission line, either short, medium, or long. Now we're going to go to solve the example. I'm hoping I can solve 3 examples. And let's start with this. I'm going to start with that one. So it said, this is let me draw this system first. So we have one generator here, they're connected to the transmission line. It has only X. This is like a short, right? Short system, short transmission line. we have a load here, SD1 is a PD1 plus JQ1, QD1. We have another load here. Now, we know this one. PD1, SD1 is, this is given. SD1 is a 15 plus J5 per unit. And SQ2 is 25 plus J15 per unit. So, if I want to know how much is the power, what should I do? Active power. I need to find out what kilowatt. Keep in mind, P is going to be kilowatt, not MVA or kVA. How much is the Q? Is a 5 times again 1 kVA is going to be 5 kilowatt. So if you want to calculate the P and Q value, you time it only by S base. This one should be timed by S base. The unit would be kilowatt. This one should be timed by S base. The unit will be kilowatt. Now, another thing it told us is PG1 limit. PG1 should be less than 20 per unit. That generator maximum can generate 20 per unit. Now, is there anything else here? The other thing is also, we want to have a flat voltage profile. Let's call this one Vs with delta, and this is a Vr with a 0, right? We want to have a flat voltage profile. What does it mean flat? It means this voltage want to be equal to this voltage, right? So this is also given. We want to have a flat voltage profile. I put it this way. I mean just the magnitude, not the angle. We want to have a flat voltage profile. Voltage from in the beginning would be equal to voltage to the end. And the other thing we say, the station loads are equalized by the flow of the power in the cable. So basically, we want these two to generate almost the same power. Now, it is asking to calculate the torque angle and power factor for each station. You want to know how much is the delta? You want to know how much is the delta? And how much is the power factor for this generator? And how much is the power factor for this generator? So when you say the power factor, calculation power factor for that generator, or that one, basically it's telling us, calculate how much is the P and Q, right? If I know how much is the P and Q, it's very simple. Remember? This is the Q and this is the P. I can calculate this, right? So basically, it's telling me to calculate how much this one is generating. The active power, reactive power, active power, reactive power. But before that, it's asking me how much is delta? How much is delta? Let's just start with delta first. So, do we have any active power dissipation here? No. This one doesn't have power, it makes it really simple. Why? Because simply you can say all the P generation, they should be equal to the all P consumption, right? P is generated here, we have PG1, PG2, right? And we have a PD1 and PD2 and PL, right? But in this case, PL is how much? 0. So basically one equation is this. I'm going to write it on the other side. Balance of power, right? So this one was very important. Short circuit capacity. Keep in mind. So balance of power is said whatever we generated, PG1 plus PG2 plus, no more plus. It should be equal to whatever we are using, right? Which in this case, because it doesn't have any resistance, P line is how much? Is 0, right? Now, to calculate how much is the PG1 and PQ1, if I know the PS and QS, right, I can write balance here. I said, okay, PG1 is coming here, I'm consuming PD1 here, so how much PS is going that way, right? So basically this one is going to be equal to this one plus this one. Here, PG2 plus PR is going to be equal to PD2, right? If I can calculate these values here, right, because this one they are known, I can calculate these values, right? And I can calculate the power factor for each one, right? Now, to calculate the PSQS, PRQR, we need the delta. We need to calculate. Actually, kind of guide us how to calculate this one. We need to calculate the delta. Now, it says we want to be equalized between these two. Between these two. How much the total consumption we have? PD total. How much it is? PD total is going to be PD1 plus PD2, right? And we don't have anything in the line. It's going to be how much? 15 plus 25. So it's going to be 40, right? Right. PG1, how much is going to be? It's going to be maximum 20 per unit, right? We want to equalize it. If PG1 was 18 maximum, we'll put 18. If it was, I don't know, 17 maximum, we'll put 17 for that. Because this is all it can give, not more than that. So PG1 20 per unit, so basically PG2 should be how much? 20 per unit as well. Because this equation should be stacked, right? Now, if I know the PG1, I know the PD1. How much is the PS? Let's write it here. We know PG1 is going to be PD1 plus PS1, right? So right here, this power is coming here, some of it is going here, some of it is going here, right? How much is this one? This is 20. How much is this one? 15. So basically, how much is the PS? PS. How much is the PS? It's going to be 20 is equal to 15 plus PS1. So basically PS1 is going to be 5 per unit. PS1 is 5 per unit. How much is the PR? Why? Because there is no loss here, right? There is no loss here. So PR also, I said PS1 now, PR, PS. So PR also is going to be 5 per unit, right? Because this one has only X, it doesn't have any R value. If it has an R value, it's going to be more difficult to solve. Now I know my PS and my PR. How much is, what was the equation for PS-PR? It's this short line with X. If you check your note, it says PS is equal to PR is equal to VS, VR over X sine delta, right? Sine delta. Correct? Now, let's say 5 is equal to, how much is the VS? 1. How much is the VR? 1. How much is the X? 0.05 sine delta. So if you solve this one, delta is going to be delta is going to be 14.5. So this is a torque angle. We asked us at the first part. How much is the torque angle? This much. Now, to finish this problem, what we need to calculate? See, PG1 we know, PG2 we know, right? PS and PR we know. What are they are not? Which one they are not known? QG1, QG2, QS1, QS and QR, right? I need to calculate QS and QR. If you go check your notes from the equation I calculated in the Saturday morning, we came here, we calculated PS, QS, and PR, QR. Or Or we can use this equation. One thing I want you to practice, this is a general form, right? This is a very general form. For the short transmission line, if I recall it, VSIS, I think was equal to was like this, right? This is what we had for the short transmission line. Look at here. How much is A? 1. So how much is alpha? Alpha. If A is 1, how much is alpha?
0.
0. So basically in this equation, wherever we have alpha, put alpha 0. How much is the A, B? How much is the B? This is the A and this is the B, right? And B for short transmission line. Make this one X, right? JX, right? If we forget, we ignore R, right? How much is the B? It's going to be X with how much? 90 degrees. Basically, B is going to be X, right? Beta is going to be how much? 90 degrees. Now, don't replace this value in this equation. You should get what we have over there. I think we calculate only for the receiving end. I think I calculate for only the receiving end. So you can calculate the sending end also if you want. You can use this equation and calculate. Now I'll use this one just for this case here. Well, I explained for the QR. I cannot memorize what was the QR. So for the short transmission line, how much is the QR? How much is the QR? Let's replace it here. VSVR over what? Sorry, yes. VSVR over what? X, right? It's going to be VSVR over X. Sine of, this one is how much? Beta is 90. Sine of 90 minus delta, what is that? Cosine delta, right? Cosine delta here. Again, how much is A? A is 1, B is X, right? It's going to be VR squared over VR squared over X, right? Again, sine of 90 minus alpha. How much was alpha? Alpha is 0, beta is 90, right? Sine of 90 is going to be 1. That's it. So, I need to calculate the QR. How much is VS now? 1 times 1 divided by 0.5 times, how much is delta? I calculated the delta over here, right? Cosine of 14.5 minus 1 to the power of 2 over 0.05, right? I can calculate the QR this way. Now I want to calculate the QS. I'll write it here. QS. Where's QS? Here. It's going to be A over B. A is 1, B is how much? Is X. So basically it's going to be VS squared over X. Sine of beta minus alpha. Beta is 90, alpha is 0. Sine of 90 is going to be 1 minus VS VR over beta. VS is 1. Sorry. VS VR over B is going to be X. Sine of what? Sine of B. B is a 90 degree, right? Minus delta. It's going to be sine of cosine of delta, right? Cosine of delta. If, let's tell me this, if VS is equal to VR, can equal to minus QS.
Yeah.
Can anyone know? Yeah, look at the word. If VS and V are not equal, right? It's going to be V square over R minus V square over X cosine delta, right? Over there is just this. So basically, if you calculate the QR here, QS, if you calculate the QS by this equation, so QS is going to be 0.638 very. So basically QR is going to be minus 638. Now we have it, right? How much is the Q line? Can somebody tell me? Q line. I'm going to write some. Q line, isn't it QS minus QR, right? We send QS here. We consume, let's put it this way. Let's say QR is QS minus Q line, right? We send QS here, consume some of the reactive power here, and the rest is QR, right? QR is the QS minus Q line. Or I can say Q line is equal to QS minus QR, right? So how much is the Q line?
1.276?
2 times this, right?
Yeah.
So we find the torque angle. We know how much is the QS. We know how much is the QR. So the last thing I need to do is to calculate the QG1 and QG2. I'm going to put this equation here. How much is the QG1? Somebody tell me. QG1 is coming here, right? Part of it is going to the load 1, part of it is going to Z. So it's going to be QG1 plus QS. How about QG2? It's going to be, see, QG2 is coming this way, QR is coming this way, so this one plus this is going to be this, right? So it's going to be QG2 plus QR is going to be SQG2, or I can say this. Right? So how much is the QD1? QD1 is 5 plus. How much is the QS? 0.638. So this one is going to be 5.638 LG. This one is going to be, how much is the QD2? QD2, where is that? Here, 15. Minus. How much is the QR? How much is the QR? So if you know the Q is the cosine Ps and cosine PR, that's easy. You know the P, you know how much is the P, right? PG1, and you know the QG1. So it's going to be, let me give you the answer then so you can look up. So I think this one is doing 0.788 lagging. And station number 1. Station number 1. I think what here is I want to say one more meaningful thing. but I want to keep the voltage fixed. If I want to compensate in general, if I want to compensate the voltage drop, they call it voltage boosting. I want to boost my voltage. I need to inject reactive power. And look at here, the generator number 2 is injecting how much? 15.638 reactive power. So this one is injecting reactive power here to compensate during this voltage number. So if they want capacitor, and who can inject reactive power is a capacitor. Capacitor can be used for power factor correction or voltage correction. They can bring the voltage down. When you install the capacitor somewhere, it's going to bring the voltage a little bit down. It boosts the voltage a little bit down. The next question, the next example, we're going to work on that. So this one was simple examples on the power flow. We cannot have a system simpler than this one. This is the simplest system. Look at how much calculation we went through. Now think about it, if you have a five boss system, how much would be the calculation? And think about it, if there is 1,000 bosses, so you know what I'm saying? There are lots of techniques, they call it power system, power flow, you explain the basic of that, but there are lots of math behind that, how you're going to solve those equations, this numerical method, you're going to use, and all those kind of things, we're not going to talk about. One more example, I want to go through one more example here. I want to keep this equation. The last example I was going to, not this one, the last one I was going to go through, I'll post it on the class. So, it's about the per unit, short circuit, those kind of things. We solved a few of them last week. I'll post that one on the class website, because I want to give you the midterm if you have any questions, I want to give you the midterm before. Now this example. It says we have a 275 kV transmission line has this parameters. A is equal to 0.85 with 5 degrees, and B is equal to 200 with 75 degrees. So we have a transmission line. The first part, it says, determine the power at unity power factor that can be received if the voltage profile at each end is to be maintained at 275. Let me translate what I said here. I said determine the power. See, we have this system. See, this is the system we have. This one has A, B, C, D, right? Here we have a Vs with delta. Here we have a VR with 0, and here we have a PR plus JQR, and here we have a PS plus JQS. It says, determine the power at unity power factor. If here is going to be unity power factor, we want to calculate how much power can be delivered here at unity power factor. What does it mean? What? Yeah. If here is unity power factor, means QR is how much? 0, right? There is no reactive power. So basically, if you want to write the question is this: determine the power at unity power factor that can be received if the voltage profile at each end is to be maintained at 275 kV. So basically part A is saying QR is 0. Let's put it this way. PF is unity, and it says we want to keep the voltage profile flat, right? And we want Vs is equal to Vr. If we have these things, how much is the P? How much is the PR? This is what it's saying in part A. Let's solve this part first. I'm going to go to this. So, basically, based on this equation, if I want to calculate this thing, first of all, I know how much is the Vs and V, how much is the Vs and Vr. Right? Because we want to keep the voltage profile flat, right? And we know the voltage source is like 275. So look at this equation. We know A, we know B, we know Vs, and yeah. This one known. Beta and alpha, they are known too, correct? And Vs, Vr, beta, B and beta, all they are known. This one is unknown, right? I don't know this one. So, can I use this equation? Actually, I should go with this one first. Because I want to calculate VR. Sorry, I should go with this. Again here, known. This one is, I don't know how much is delta, right? And the rest they are known. So if I knew how much was delta, it was very easy. I can calculate it, right? How to calculate delta? This equation. How much you are? Known. This one is not, we don't know how much is this one, right? But the rest, they are all known, right? A, B, beta, alpha, everything is known, right? If I use this equation, I said QR, I'm not going to write it completely, but I'll write part of it. QR is the Vs, Vr over V, I don't know, sine beta minus delta, let's write it. Beta minus delta minus A over B, Vr squared, sine beta minus alpha. Here the problem is not period. It didn't say anything about this one. No. It didn't say anything about period. Just replace the values here. So how much is the B? How much is the B? 200, right? How much is the Vs? 275. How much is the Vr? 275, right? How much is the beta? 75 dB. Okay, delta, I don't know how much it is. How much is the A? 0.85. B is 200. Vr, 275. Beta, 75. Alpha, 5. Right? If you replace these values, how much is the QR? 0, right? Because we said we want to deliver the power at unity power factor, right? Just replace these values here. Is there one unknown? Is delta. Very simply, you can solve it and you get the number. Delta is going to be 22 degrees. But it didn't ask us to calculate delta. It told us how much power we can deliver. How much power we can deliver over there, right? So I use this equation now. Equation number, I'm not going to write it down. I use the delta is 22. Delta is 22 degrees, right? And equation 1. And I usually get 1 so I can calculate the PR, right? Because everything is known, right? We got here Vs, Vr, V, beta, delta, A, B, Vr, beta, alpha, everything is known, right? Just replace it into the equation. If you do that, you can calculate the PR is going to be 117.7 megawatts. So this part was part A. Part B, asking, see, remember in the previous example I showed, I said to keep the voltage profile flat, right? I said the generator has to inject reactive power. It will act like a capacitor, but it does have active power also. You know, one of you asked me a question one of these days, you know. He said, what is the synchronous condenser? You may hear the name of that. Synchronous condenser is a synchronous machine, only generates Q. It's designed to only generate Q, reactive power. It doesn't generate any active power, only Q. So, can you guys tell me what's that? Maybe not because you don't know how the synchronous generator works. But maybe you ask, okay, so if it's just reactive power, why you don't use a capacitor? The main difference between a synchronous condenser and the capacitor is a discrete. You can put this much capacitor, the Q is going to jump. It's not going to be continuous. You know what I'm saying? For example, your Q is going to change this one. So if I put this much capacitor, I have this much Q. If I put this much, I have this much Q. This much Q. This much Q. You know what I'm saying? But the synchronous condenser, you can do it this way. Continuously, you can select any number to do, which is much more expensive than the capacitor. Very, very expensive. Power electronics has solved this problem. They call it SVC. If you are interested, just Google type this. SVC. They call it a static var compensator. A static var compensator. It works exactly like a synchronous condenser. There is an inverter and there is a capacitor. Just to let you know, in power electronics too, we talk about this one. Inverter and there is a capacitor. And here we have a Q. You can either inject or absorb Q, either way. So now going back to this example. From the previous example, we find out if we want to keep the voltage profile flat, we have to inject reactive power. In the previous example, the generator number 2 did that one. Inject the reactive power to the bus to keep the voltage constant. In this case, we don't have a generator. Now the question is this. What type, first is asked, what type and rating of compensation equipment would be required? It said, first of all, tell me, to get this thing, I want to have a 275, 275. Tell me what should I install here? And capacitor. So the answer, I'm not going to install generator because it's expensive, right? I'll go with my cheaper choice. I'll go with the capacitor here. But he's saying, tell me how much of rating, tell me how much the capacitor should generate. What's the rating, Q rating of the capacitor? He's telling me, tell me what type of equipment? We said capacitor. But how much? We need to calculate that one. How much we're going to put there. What type and rating of compensation equipment would be required if the load is 150 megawatt? Now, in second part, if we have this much load, looks like we don't need capacitor. We are good. Now we are going to go to 170, 150 megawatt. If we go to 150 megawatt of load, we want to see how much capacitor we should install here. To keep the voltage profile fixed, for the second part, I have to install capacitor here. To inject QC here. I want to calculate this one. If this is part B. Part B. Still I want to have Vs equal to PR and PR is going to be 150 megawatt. 150 megawatts. At unity power factor. Still I want to have a cosine CR to be 1. So what does it mean this one? Let me put it this way. Okay. Still here, I want to have a unity power factor. 1. Basically, still QR is going to be 1. But this guy, we need some reactive power here. This guy is going to inject the reactive power as well. So we're going to calculate that one and see how much it is. With the same voltage profile as before. Yeah, 275. We're going to have this one 275. 275. Now we go to this part. Again, QR is 0 here. So I'm going to do this. I know PR, right? I know PR is 150 megawatt. I know VSVRB, all these kind of things. I know how much they are. So I can go calculate my new delta. Look at here. How much was the B? Beta we have it over 75. Delta, I don't know how much is it, but I know the PR, right? So I'm going to use this one. I'm going to write it down, right? 150 megawatt. I'm using this equation. I want to calculate my delta. 150 megawatt is going to be equal to 275 to the power of 2. Because Vs and Vr, they are equal, and each one they are 275 kilowatts, right? How do you do PR? It says, it's asking if we are going to deliver 150 megawatt here at unity power factor, and we want to keep the voltage profile flat. These are all given. It says what type of equipment we should install here, and how much is the rate. You know, we said the answer is capacitor or synchronous condenser, but forget the synchronous condenser because that's very expensive. We'll put the simple capacitor here, right? And we said, okay, how much? How much should we deliver? See, we are solving this one for single phase, but this is a 3-phase system. You find everything later, if you want, by 3 to get the final number. So it's going to be this divided by how much is B is 200 cosine of 75 minus delta minus A is how much? A is a 0.85 over B is 200 times 275 times to the power of 3 to the power of 2 cosine of 75 minus 5. So if we solve this one, again delta is going to be 28.46. So to deliver 150 megawatt here, we should have that much torque, right? Just look at it. Previously, how much was it? Was 22. I want more power. I have to increase it. See, just go back to the short line. P was Vs, Vr over X sine delta, right? This is very similar to that one. These are all fixed, right? If I want more power, right? Here, how much was it? Here was 117, right? I want how much? 115. What should I do? I should increase delta, right? So basically here, how much was it? 22. Now is how much? 28. I have to make it open the delta, right? Now, we calculated delta. We calculated. Let's calculate the QR. If we didn't have capacitor, think about it this way. How much QR we're going to have here? And after that, we say, hey, we should have not any QR, right? I replace it with capacitor, right? So if we calculate QR, no cap, let's say no cap. If we didn't have any cap, if you did another right, you replace all these values here, you know, the delta, Vs, Vr, A, E, alpha, beta, delta, all those kind of things. If you replace all these things, the QR is going to be minus 2756 megawatt. See, if we consistent load you are using. Minus means we have to generate, right? So what should I do now? If I want this QR will be 0 here, right? See, right now it said, hey, minus this much. Minus, I don't know, 27. So I'm saying, hey, don't go there. I'm going to put capacitor here. This capacitor is going to cancel this one, right? Basically, Q here will be 0, and this capacitor will be 27 or whatever. So, with cap and QR0, so basically QC should be 27.56. Right? I calculated how much Q, if I'm going to have a flat voltage with 150 megawatt, Q is going to be this much. But I'm saying no, I want a unity power factor. See, I have to generate this much with something else. I put the capacitor, right? So I think we're going to stop. Finally, we'll upload one more example or one or two more examples on the calculating things and those kind of things. In your book, chapter 3, there are some problems about the pyramid system, but not the short circuit. If you want to practice more, it's there. So, guys, sorry if I was sometimes a little bit, picking on you and a little bit, maybe a little bit angry. I'm sorry about that. And hopefully you guys will do all very good in your final. Okay. Matija